Okay, hi everybody. I'm Eduardo from the UAB. And before starting talking about what I have prepared for today, maybe a little bit of context would also be useful here. So how apart influenced us and our group to do the things we have done in the last 25 years. It is to say that the main researcher that was involved in the APART project from our side was first Emilio Luque, who is now retired since 8 years ago, 9. But he's still going every day to the university, every day. And he's still in charge of many things with part of the group. Although he has been involved in doing some tools, they have developed Pass2P tool, which is also it's a tool for doing performance tuning and things like that, or performance characterization of applications. He has moved more to the simulation, agent-based simulation of things related to health systems, hospitals, and things like that. Okay. So the second person that was on that group, I mean, more significant, was Tomás Margalef, who was really on the tools and modeling side. But Tomás started moving to other things, maybe 2010-12, and he's now completely dedicated to the simulation of forest fire. Things like climate or weather forecasting or micro weather forecasting, but things like that. And he has no relation, so he has been working on development of parallel things, on optimization of this kind of simulation, but not in the tools or modeling lines. So there were a couple of persons. Well, there was also Antonio Espinosa, who was at that moment near finishing his PhD thesis, but he, at the end, when he presented his thesis, he left the group and he went to the private sector and came back several years later. So he's also in another research lines. Many research lines. So I won't talk about which kind of things he's doing. But the other two that were in that group, one of them was Ana Sicora Anya, who was recently incorporated into our group. At that moment, he was very, very young, and he was like in the research, looking for something to do for her PhD dissertation, and he was really inspired by the tools thing. And she decided to start working on a tool. And this tool was called MATE, Monitoring, Analysis, and Tuning Environment. And it was a tool that was based on plugins. But the idea of the tool was it was able to somehow instrument a group of MPI processes, get some measurements, some data from that processes, and analyze this data, and during the execution take some decisions in order to improve the performance of the application on the fly. And it was, as I said, that was a plugin-based tool, and the plugins describe what to be measured, how do you analyze this information, and which actions you can take in order to improve the performance. So something important about this tool is that you need to program these plugins, that you need the models to do things and program these plugins. And this is where I go in. I was also at the moment looking for something to do for my PhD dissertation. I was had a little bit more time in the group, but I haven't found what to do. And then I was interested in the part of the models, and I start working with defining performance model for some kind of applications, and try to collaborate with the tool, with the Mate tool. So, as you can see, Anya should be the one here talking here because she was the tool girl. Okay, I was in the modeling part, but she had more hours of class this week than me. So it was difficult for her to come, and she doesn't like to talk in front of, only guys. This is a, there is the problem that we were discussing yesterday, no? with the presentation. She feels alone in this. Well, so it's just joking. So anyway, all these things, so we make with our dissertations, and all these two lines just progress during several years in our group. So we were generating models. In my case, the models that generated at that time, beginning of the 2000, things were really easy to model. You don't have multicore, you don't have complicated memory hierarchies, and you have MPI and the network, nodes, and so on. So, for example, modeling master worker, we called master. We were already calling master worker, not master slave. I saw that yesterday in Bern presentation was the old times when we were calling that master slave. Not it was politically incorrect. So even though nowadays master worker is also politically incorrect. But okay, I generated a model, very, very fine-tuned model for this kind of applications, and also I started generating models for pipeline applications and so on, and they worked quite well, and could be integrated in Mate somehow for some examples, and everything was nice. But then during these years, we keep working on models, and the hardware started to become more and more complex, and the models started to become more and more impossible to define analytically, at least. No expressions at all. Maybe some heuristics, maybe some algorithms to solve something, but no expressions at all, for general cases, at least. And in the side of the tools, Anya keep also working with other people, generating new versions of Mate. The important thing was that we ended up like in 2014 with the last proposal for having a scalable Mate that could run in really big systems. And the last modification of this tool was in 2017, when we incorporated the ability, we made a small modification to incorporate the possibility of Mate gathering performance counters, because what I am going to explain now, that was a moment that working with models was just impossible. We were getting not good results. We were investing a lot of effort in defining models, general models that were not working very well. So we decided to try doing something with machine learning. So let's see if we are able to generate some models, but machine learning models that could do some performance tuning, okay? So that's what I'm going to present today after this long introduction to put the things in context. It started more or less at 2017, okay? And of course, the motivation was this. Systems are so heterogeneous, so complex nowadays that are very complex it is almost impossible to do modeling of the systems. So let's try another way. Let's try another approach. Okay. So at the beginning, it is. I mean, you do these kind of things, and you can do these kind of things because you are in academia. Because I mean, you don't really know a lot of what you are going to do, and machine learning is not our expertise. So we just say, okay, let's try it and see what happens, okay? And we just say, okay, let's see if we can just find some features that characterize parallel applications, and let's see if we can define create a data set and train some model that can be used later to do some performance tuning of applications. And this matches more or less the idea of Mate, because you can use the model, you can integrate the model in that one of these plugins, you can take measures, you can measure something from the application at runtime, and then apply the model to do some tuning, okay? So as far as we are a very small group, we had to focus in just one thing. We were not able to take a wider look. So what we did with our PhD student is we said, okay, let's try with OpenMP. And not everything in OpenMP. Let's try with parallel loops with OpenMP, okay? And our hypothesis was that we can use performance counters. That's why we integrated we created the possibility with Mate for measuring performance counters. We said, okay, let's make the hypothesis that we can use performance counters to characterize OpenMP parallel loop applications. Then let's create the data set, train the model, and so on and so forth, okay? And it was funny because the guy that was working in this PhD its main topic in the PhD dissertation. Michael was in the committee. It was a very hardworking guy with several ideas, but it was very funny because every time that we started something of this, he came to our office, some place, say, we have a problem. Always you got some problems, and it was funny because it really happens that you have a lot of problems to do that. So let's start with the metrics. So with the features, okay. So the thing is that in any architecture you have many performance counters, which several flags for each of them, and then it is non-feasible to say I want to measure all the performance counters, okay? Because you have to use multiplexing because you cannot measure at them, of course, at the same time. You can only measure a few of them, and if you use multiplexing to measure the performance counters, then you're losing a lot of precision, especially when the size of the problem is not very big. And of course, you need much more executions in order to get all the data. You need to do the data analysis and things like that. So what we said in this case was, okay, let's try to find a way to decide which is the set of performance counters that can be used in order to characterize the parallel regions without losing many information, but a reduced set of performance counters, okay? So this, our student started working on that. We were starting this research, so we started very simple things, okay? And then the idea was that, okay, we could measure do some data collection on a reduced set of examples. And then the idea that we had at the moment is that we could use principal component analysis in order to visualize and analyze the data and see if we could find, if this analysis hints some redundancies among the different performance counters and so on. And then after that, we used correlation in order to decide to find performance counters that were really correlated. And if they were really correlated and the correlation could be explained, then we manually decided to just eliminate some of these performance counters. So it was basically a manual methodology. It was systematic, but with a heavy intervention from the user, okay? So for starting, we use the stream benchmark, which is only 4 different parallel regions. So 4 different force loops, simply. We use a couple of different optimization flags. Our student defined it more or less randomly. I mean, it's sensible, but the sizes that he decided, the problem sizes were more or less randomly defined. And he decided to do 1,000 repetitions of each of the executions in order to have a statistical validity, which is a lot of repetitions, much more than necessary. But at the beginning, okay, we were somehow just testing. And the thing was not bad. We see that PCA really was showing the data with only 2 dimensions. You can see the 2 optimization flags. You can see the different sizes for each kernel and things like that. So it was fine. And you can describe most of the variability of the data only with 2 dimensions, okay? So then using the correlation, we were able to start, eliminating counters just because they were composed. Some counters were the composition of other counters and so on and so forth. So we were able to eliminate many counters, and at the end we finished with 20 performance counters, and we see that we still are seeing the data, so these counters are explaining the data, and although there was already some strong correlations, we could not explain them, so we keep all the 20 counters and stop. So we did some iterations until we get a set that we was satisfied with. And to test that this was okay, we just trained a neural network using the reduced number of counters, and we saw that, of course, we only had 4 different loops, so it was not so difficult to have a very high accuracy, but we were happy. So it seems that we can go this way. It started to be a promising thing. So we decided to pass to the second step, which was building the data set. And here we also found that there was a problem. You cannot simply get every 4 or parallel 4 in OpenMP, just get the counters and put them and put this data in the data set. Because it happens that several different 4s, different parallel regions, are the same thing or are too similar between them. So if you are introducing all this data in the data set, you are unbalancing, you are getting an unbalanced data set because there is an overrepresentation of some kind of this region. So we wanted to build a balanced data set, and oh, this thing was looking better in my computer. So okay. So anything in this case, what we did is we define for the problem sizes, we define in a very systematic way for a specific architecture, which were the problem sizes that we were going to test depending on the number of cache levels, size of cache memories, and so on and so forth. So we developed a systematic way of defining the problem sizes, no more random problem sizes. We executed all the cases that we were going to consider for every possible number of cores. We were using different affinities, and we also computed which was the number of repetitions that we have to do to have statistical validity. And this, with 100 repetitions, it was more than enough, so we reduced the number of executions. And then we defined a new method, in this case, where you take the parallel region, so the 4 that you are going to parallelize with using OpenMP, and you execute this thing, this candidate for a certain problem size, which is a regular number size, not too big, not too small, we get all the performance counters, the 20 performance counters that we have decided that were enough in the architecture we were using in this case. And then once we have this data, we organize this data somehow and correlate this representation to what we already have in our data set. And if we find that there is something very highly correlated, we could decide that this for this region is already on the data set, so we can discard it. And if we don't find that, then is when we execute all the possible combinations. We execute for all the number of cores. We execute for both affinities. We execute for all the problem sizes that we have determined. And then we build the representation of this region that we consider that was a region that is, so if we consider that there is a region, there is a space of different parallel regions in OpenMP, okay? So when we didn't find this correlation, we say, okay, we have found a new part of this region that is not already represented in the data set. We made all these executions and introduced the data in the data set, okay? So that was the main idea. And what we did is on the same machine that we tested the reduction of the number of counters that were needed to represent a region. Now we used the stream for patterns, and we extracted 29 more patterns from the polybench, and then we applied the methodology that I have just presented, and doing this, we found that these 33 different force, or parallel force, could be grouped in only 8 different types of patterns. And then we choose the most representative parallel region of each of these types, and this was what we introduced in the data set. So we reduced the 33 different regions that we have been considering only to 8 of them, okay, to build the data set and have more or less a balanced representation of each of them. To test if this was working, we again trained a neural network, and we trained the neural network using the 33 different patterns, the 33 kernels that we were considering, and trained it again, created a second model using only the 8 groups that we have obtained from applying the methodology. And then we got from the NAS parallel benchmark some kernels, some parallel regions, and just used that in both models. So in the model, in the case we were using the 33 different cases, we can see that the same kernel, the same region from the NAS parallel benchmark, sometimes was classified in a way, sometimes was classified in a different way. Okay. In cases like this one, the first one is not so bad because add and scale were both in the 1D group. So, okay, it's not exactly the same, but at least everything is in the same group in the same pattern. But sometimes reduction was a different pattern than 2D stencil, and we have all these conflicting cases. No, when we have this dual classification, sometimes it's a reduction, sometimes it classifies a 2D stencil. In this case, with a balanced data set, every time it was classified as a reduction, and so on and so forth. So it looks like it was okay to do this, to generate the data set using this approach, okay? So, say, wow, now we have it. We know how to choose our performance counters. Now we have created our data set. Let's go for performance tuning. Let's train something. Let's train a model to do performance tuning. Yes?
You have these patterns.
Yeah.
Are these patterns parameterized?
In which?
Like a vector, the vector size, the 2D.
Yeah. You have, for each pattern, you have all the, so you have the measurement of the performance counters for every size, which was determined systematically for the architecture you are working with. So you have for small problem sizes up to problem sizes that were passing all the, we were stressing L1 catch, L2, L3, and then going into main memory. Okay, so we have all these cases. We have this information for one core, executing the application in one core, in two cores, in three cores, and until the number of cores of the architecture. And you have that for round-robin affinity and for the other one, close affinity or something like that. So you have all this data for each pattern in the data set. Okay, that's the idea. So yes, and you can add more parameters. We have been doing that lately, but at the moment, I mean the problem here is what yesterday Felix was mentioning. Executing that it's painful. I mean you need months and months to get all this data when you don't have Mare Nostrum for doing that or something like that. Okay. Nobody lets you to use supercomputing for this. So okay, but the real frustration came here. Our PhD student, just got Keras or PyTorch or whatever, and he just trained all he could find in order to tune the number of threads. So decide which was the best number of threads for a given. So you have a given values for the 20 performance counters that we have been considering, and tell me which is the best number of threads for this application. Okay, and yes.
The best suggests as one criteria or one unified criteria.
No. Execution time, okay? The criteria was the one that optimizes, that give us the minimum execution time, okay? So he trained a lot of things, and you got these suspicious 100% for many of the cases, which is not very nice. But the worst thing came when we test the models that he generated, and you can see that we were getting very low accuracies. So it was like, what's happening here? What's the problem? That we are having? Why are we are not finding good results here? And what we thought at that moment was that we were so bad. We said, okay, we have created a representative data set of different patterns, okay, which is balanced. But for a given pattern, for a given class, you have that most of the times, okay, you have some number of threads, which is best for many of the different cases that you are representing on your data set. So what we thought at the moment is that we have an imbalance a natural imbalance in this case, when we came to trying to find which was the best number of threads to execute a certain case, no? And then we were, focused on trying to solve this imbalance somehow, okay? And well, of course, you can try undersampling, but if you do undersampling, you are losing the representativity of your data set, which is not a good idea. You can try oversampling, just replicating the cases that are underrepresented, but this was not working at all. We tried generating some synthetic data using Smooth or other techniques, but then even though you are generating points that are closer to the ones that you have in the data set, you don't really know if the data you are generating makes any sense at all. So at the end, what we were trying was to use some algorithmic methods and some ensemble of of machine learning models, which were the thing that more or less give some results. But you have to understand, well, I know you understand, you're in the academia. So this guy was finishing his PhD, the grant was depleted, he had the visa to go to the United States because he was going to work with Samir in Oregon. So we had to finish that, and then he just say, okay, let's try to get good results. And he considered, okay, when the model was able to figure out which was the best number of threads, we'll say, okay, but it's also good if the model predicts the second best number of threads. And at the end, he ended saying, okay, and even if we don't find the best number of threads or the second best number of threads, let's see if the output of the model at least is efficient, whatever it. I mean, we have an index for measuring efficiency here, and this was the idea. Why do that? Well, we have here the base cases. We took the best model, which was decision trees, which was better than artificial neural networks, even though we see that there are cases that are very bad. Decision tree was our base, the comparison, our base case. And then we train a random forest in order to see how it improved the base case. And we are improving.
Well, can you tell me what makes a bar good or bad?
A blue bar, it's excellent because the model is always saying for every case, every time that it finds a reduction, it is saying the best number of threads for executing that reduction, okay? But you see that there are several cases where the best or even taking into consideration the best or the second best is incredibly low. So, okay? With random forest, you get a little bit better. And with binary random forest, some of them get a little bit better while other go worse, okay? So, okay, we knew at that moment that we had a problem, a real problem in this case, because we were not, we have focused, we were trying to solve a problem that in the wrong way in this case. Anyway, he finished his work, and then we keep working on some of this stuff. And I want to conclude basically saying what we are doing now with that. No, so some kind of evaluation, like what Bernd doing yesterday, for the part of reducing the number of performance counter needed to characterize a parallel region. The good thing is that we saw that it was possible to do that with performance counters, but maybe the methodology that we have defined was not so scalable, and we know that for sure, and it's not fully automatic. That's a bad thing. For building the data sets, okay, we were able to build the data sets, and I think it was good. The problem is that it's painful, so you have to execute so many cases and spend so much time doing that. Is there anything else that we can do not to run everything so many times? And of course, from the performance tuning part, we were expecting better results, so something had to be done here. So since then, we have generated some more complex data sets. We generated a data set for a most modern Intel processor with 32 cores, and this is finished, this is done. We have a huge data set for that architecture. We tried also with an AMD with 64 cores, and the problem here is that PAPI doesn't work with AMD processors. It's just a mess. And then we moved to Liquid, which is quite good in this case. But the problem is that apart from having to execute a huge amount of cases, Liquid is slower than Puppy for gathering the data. So we are having, it is still executing, and we don't have this data set ready yet, okay? But we have now a much interesting data set. From the signature reduction methodology that we proposed, this is not on the data set from data because it was not complete by the time. But we started a collaboration with a guy from the Czech Republic, and he passed us some information, some cases, some data sets measured on GPUs, because basically you can apply all of this also to GPUs, okay? So which is interesting. But when we try to visualize things on the GPU and do correlation analysis, it was like, okay, come on, we can do that. We can't do that, okay? So the guy that is working now on that, it's more, he has more formation, it's more educated in machine learning. So he found this way of building ensembles of machine learning methods, but in this case, he's using very different methods. So it's using linear regression, he's doing random forest, he's doing XGBoost, which is kind of also decision trees. But in this case, you don't have many decision trees, but one after the other, each one of them improving the previous one. He's using also neural networks and so on. And he has devised a very nice method for them to decide which are the counters that are important for each of these machine learning methods, and weighting them according to the accuracy of any method. So we are getting a group of performance counters, and then we are doing this elbow or knee analysis for determining how many performance counters are really needed to classify, to represent parallel regions. So this is something that he has done. And about performance tuning, we were assuming that the problem now we think is, we were assuming that the same counters that are good for classifying a region were good to tune performance parameters. And that's not necessarily true, no? I have counters that say what is this region? What is this region similar to? But not necessarily these same performance counters are useful for deciding how to make a prediction for the performance parameters. So what we are proposing is doing this same kind of ensemble of methods, but for regression in this case, and we do classification in the case of knowing which is the pattern of the region. But now we can use the same ensemble for determining which are the counters which are the best for predicting every tuning parameter for every of the cases. So basically every pattern. Okay. So at the end, our general scheme has changed a little. So we are getting the data, and we are using this data on the one hand to create this prediction, this classification model, which is able to give which is the pattern given the application. So we have a set of performance counters that are used to determine which is the pattern, and knowing the pattern, we have for each pattern and each tuning parameter, we have a model that knows which are the performance counters that are needed to do the prediction related to this tuning parameter. And this is the model that is giving us the value.
So I understand how you decide which counters are good for prediction, but how do you decide which ones are good for tuning? But doesn't that require actually to go through a step of using them to do tuning?
Oh, I think afraid I don't understand, because what I'm saying here is you have a set of counters, and this model is giving you the right number of, for example, threads for this application.
So, okay, that's the two.
Okay, so you have the result is which is the tuning that which is the best value for this performance. For this tuning parameter.
So you have a fixed number of tuning parameters.
Yeah. That's something that we are also doing several things around that, but and we haven't published that yet. But the results that we are getting are much more promising than what we got in the previous case. No. So it looks like we are getting where we wanted in the moment. So just for this, a small word, which is the parallel region. So, but that has been working, and it's nice because we are being collaborating with Ali Hanesari group at Iowa State, because they are using some of them, so they have this multimodal modeling and heterogeneous graph neural networks for doing performance tuning. They do that the graph representation of the structure of the region and an embedding of the semantic that represents the semantics of the region, but they needed some data that somehow described the dynamic behavior of the code for a certain data size, and they are using, of course, they found that using our performance counters, the performance counter that we are determining is right for doing so, and we are collaborating with Jiří Filipovič at the Masaryk University in the Czech Republic, because he is interested in doing something similar for GPUs, which is his expertise field in this case. We don't have a data set for GPUs, but he has a slightly different approach, so it can be useful for him also. So, thank you. Oh, it was so quick. No? More or less. No. So, just for the dinner. Thank you. So, any question?
So your feature space are performance counters.
Now.
And it was interesting you mentioned the Iowa State work, because I was going to ask you, and you've had some challenges with that feature space. I have a question. And the Iowa State people are using static code characteristic features.
Yeah.
Because that was my question, is saying, have you thought about the analysis, trying to drive it, from the OpenMP constructs and things like that to drive features that...
There are several things that can be tested. Yeah, you're right. We have found sometimes, for example, we were discussing that, and some guy said, why are you using, for example, information from the operating system? Okay, that can be also very, 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 very useful.
But that's more dynamic. So I was
interesting
to, a performance count can be anything. It could be page fault counts. It could be
anything.
Space size. So that fits in the methodology.
Yeah.
I'd say something really different, like static code characteristics.
Yeah. They are using that, and it is also working. So of course, this is part of the sense of this collaboration, is that they are using our dynamic approach, and we can think of ways of using their static part in order to, for example, do classification in a better way. So something like that. No, so with the information about the structure of the code and the semantics, the embedded of the semantics they do, it's much more easy to determine which is the kind of region you're working with. No, so maybe you can use that.
But how can you change this static structure in order to tune the performance?
I know.
What would you propose?
The various parameters used when you do the OpenMP, when you specify loop structures and nesting.
Yeah, this is fine, but I thought you made something different and somehow independent of what you do at the level of OpenMP, just
What
relates to the code structure or the assembly operations that we use.
Well, then you're wandering in the compiler optimization world. Yeah. So that's a whole other complexity which I don't wish under.
Actually, that was my question as well. It's like, when you collect all these things, I know you talk about different compiler flags and affinities, but different generations of the same compiler will make different predictions and different optimizations, even you use the same flags. And even if you switch the flags around, everything is different. Is that something you all will try to do in the future?
Not at all. So at the beginning, we're using different optimization flags. Why we just use 0 and 2? Because if you use 3 in this case, for example, the functions disappear. No, they were inlined, and then how you take measurements in this case. So this is we haven't considered that.
But I think you should not only target to find the best value, right, with your tuning model, but it would be very helpful for auto-tuners to have a guess what could be good settings, right?
Mm-hmm.
And so they don't have to go arbitrarily through the search space, but they get some guidance from your models. Yeah, also you don't know the best one,
Mm-hmm.
yeah, but you can identify the good ones.
Yeah.
That would help a lot, I would say. Huh?
That's something that is in the collaboration with the Czech guy, with Hiri, because he's very interested in pruning the search space. Okay, so he's very interested in, you have a search space and say, okay, let's see if we can eliminate most of the bad configurations and keep the good ones, and identify if we can add, if we are missing some good ones in our configuration. No, so that's something that can also be done through the performance counters, because he tries to relate how the performance changes with the changes of the performance counters, and how to relate the change in the performance counters to the change in the tuning parameter values, something like that. So considering only the performance counters that are really influencing the performance of the application, because they change the tuning parameter. Well, something more or less complicated in this sense, but this is the idea. Okay, just look for a good search space when you have more good configurations, and then it's easier to find what you're looking for. No?
Do you remember Robert's approach? Because he spoke about Robert, right?
Yeah.
So we actually try to get rid of all that you actually have to search for the signatures of the performance counters. But instead of that, looking at the sensitivity of the code for certain tuning settings.
Mm-hmm.
You have your tuning parameters, you select certain settings, and you look at the effect on that code that you want to tune.
Mm-hmm. Mm-hmm.
By that, you can now put it into a class and say, yeah, it makes sense to tune it, or I want to have these settings, I try these out, and so on. Right? So he got rid of all that you actually have to search for the signature.
Yeah.
Just trying to use some of these tuning scenarios to identify the sensitivity.
Mm-hmm. Mm-hmm. Yeah, I think this guy is looking for that. He's looking for that. Yeah.
So you mentioned you've looked at number of threads and things like that. Are you also looking at other things like the blocking size and things like that?
We are considering scheduling policy, chunk size, things like that, for example.
The reason why I ask is because you use Polybench, and I know Poly has an analytical model. If they recognize that, oh, this fits matrix multiply or matrix vector multiply, then it will swap in the appropriate model for that class of models. And so that seems to be a good way to compare and contrast different methods.
Felix.
Just a comment, so Ali Janissari was a postdoc in my group.
Yeah, I know.
Give him, please give him my regards.
Yeah, thank you.
have a question. I may have missed part of your presentation, maybe, but the time it takes to build these models. Can I impose a constraint like, okay, start building your model, but in 2 hours you should finish, and then whatever the model can deliver, it delivers. Is this possible, or it's all or nothing?
This is a different approach. So I haven't talked about related work here, but this is a different approach. No, I think it's Artemis. This is a very nice group in some of the labs. I think they have something called Atlas, which is something for changing, so deciding things like when you could offload the work to the GPU or decide some parameters on the CPU or things like that, and they do that. Their idea is they measure some performance counters at execution time for the application they want to tune. They don't have a data set. They measure some performance counters in the first iterations of the regions. They train a they do a quick training of a decision tree or random forest with only 2 levels or things like that. And they claim that using that, they train on the fly models very quickly that are able to take these decisions.
Yeah, but you run the codes multiple times.
Oh yeah,
parameters.
but not the code that I want not the code that I want to tune. All the multiple executions and things like that is.
This I understand. What is a typical time it takes you to build a model? Like days or 3 weeks, or what is it?
No, for creating the model, it's not so long. I think with a few hours we can create something. But the problem is all the executions that you need to measure the performance counters that you want to put in the data set in order to be able to train the model.
I still will find it because in some sense you consume energy. These are some costs if you do it on the cloud. It would be kind of nice for all these models that you explore that I can say, okay, all these models that you explore, you have like 12 hours or 4 hours time, and whatever you derive until then in terms of model quality or accuracy is the same time. Consider that as well.
No.
Because different models probably took longer.
Yeah, sure, but I don't think that this is the so creating the model is not the painful thing. It's running, it's getting the data, it's gathering the data. What we are investing, like I just say, a lot of energy, real energy, because for the Intel case we have been executing like 1.5 years.
Yeah, but still, I would say it's a valid research question. Like if you build a technique, build a model, and I build a model, and Michael, and then we say, okay, everyone has a certain time, and then or you use different time, and then we compare in terms of accuracy, but also the time it took.
Yeah, of course.
If yours has the best accuracy, but it takes you 7 days, and mine it's not so good, but 2 hours that has a value.
Yeah, you're right. You're right. Yeah. Somehow. There are many things to be considered. Okay.
So the PhD student completed successfully.
Oh yeah. The previous one, Michael was in the committee, and the student passed. So.
The operation was a success, but the patient died.
Yeah.
It's a small one, I think it's okay.
Okay.
Any more comments? No. Let's thank you.
Thank you very much.